been working on here for about a decade, I guess. It's headed up by Paul Nielsen, who's a principal investigator here at the ABI, and myself, and we've had a range of graduate students and postdocs who've worked on this. So our primary goal is to provide software tools to help with breast cancer imaging, diagnosing breast cancer, but there's a whole bunch of other, that's how we got into this, but there's a whole bunch of other applications that we've touched on along the way, and I'll come back to those kind of at the end. So for the purpose of this talk, I just wanted to show you guys how we're using some of the software tools, some of the biomechanics software in particular, to address a clinical problem. And so just a very little bit about breast imaging. It involves a number of different imaging modalities. So the most common is X-ray mammography, and it's the most specific form of imaging that can catch, well, I mean, I guess we talk about it in terms of false negatives. How many cancers does it miss? And so the best kind of statistics for mammography is something like catching 80% of tumours which are less than, well, 10 millimetres or less, I should say. So it's still not perfect, but it is the best imaging modality we've got. There's lots of problems with it. It involves X-ray radiation dose, for example, very low X-ray radiation dose, but it's still the best imaging procedure that we have. If I'll show you some mammography images as we go through, but one of the classic sayings that goes along with searching for breast cancer and mammography, it's kind of looking for a snowball in a snowstorm. So you'll see what I mean by that when we deal with some of these images, some of the difficulties with these images. If they spot something in mammography, then typically they'll send it for something like what they call second look ultrasound. So they'll have a ultrasound probe that they'll put the patient on their back and hold the ultrasound probe and start hunting around for this suspicious lesion. They might use ultrasound to place a biopsy wire so that they can take a tissue sample and send it off to the lab to determine whether or not it is actually cancerous tissue. The other modality which is in common use, particularly for things like guided biopsy, needle biopsy, is MRI, where the person is lying on their tummy and the breast is hanging down between two specialised coils. So I guess the reason for showing you these pictures is that you can see that the breast is in very different positions, so large degrees of compression with the person standing up, or the breast hanging freely down in the vertically downward direction in these coils, or the person lying on their back and ultrasound probe being pushed up against the breast. There's very, very different shapes, different positions, and perfect for the engineering analysis of soft tissue mechanics. Why is it important to do this? Well, it affects a lot of people. I know several people who've suffered from breast cancer, a few that have died. These are, personal friends. Lots of us have got some sort of connection to breast cancer. The key thing is that finding these things early leads to better outcomes. So if you can find these masses, particularly if they're less than 5 millimetres, then the prognosis is really good. But the problem is that finding these things is very difficult, and they can go unknown. A very good friend of mine, she was a fairly large-breasted woman. She had an 8 centimetre mass that she didn't know about, and she's had a double mastectomy now. And this is the sort of thing that can happen without realising it. Now, how that got missed is really unclear, but the imaging failed, or at least particularly in younger women, the imaging is difficult because they're dealing with dense breasts, so the fibroglandular tissue looks like cancerous tissue on the X-ray images that they look at, so it's very difficult to spot these things. And so lots of different imaging modalities, lots of different positions. What the clinician is trying to do is to take information from each of these imaging modalities and bring it together in terms of a three-dimensional view of what the breast looks like with all of these different bits of information. So X-ray is good for dense tissues, I mentioned this yesterday. MRI is good for soft tissues and things like blood flow. Ultrasound is good for differences in tissue densities as well. So they tell us different information. The breast is in very different positions. Can we bring all of that information together in a common 3D visualization environment? And can we use the laws of physics to help us do that? So it's difficult to do this just based on the imaging features alone. There's a bunch of groups that are out there just trying to use image registration techniques to be able to take these images from these different modalities. But because we're dealing with very large deformations, those image registration techniques, and also images of very different types of contrast, those image registration techniques are typically fail. They're very, very difficult for these large deformation, different contrast problems. So we're adopting the approach of using the laws of physics to basically help us get a better registration of the information, and then potentially using image registration, non-rigid registration techniques to be able to fine-tune it from there. So that's the area that we're looking at. And just I think I might have shown you some pictures like this. This is roughly what an X-ray mammogram looks like. There's two different views, and I'll come back to this idea of the sort of stereotactic nature of mammography. But the sort of thing that X-ray mammograms are good at looking for are the things like the dense tissues, whether it be cancerous or whether it be fibroglandular tissue, as opposed to the fatty tissue. MRI, very, very good for soft tissues. Again, the difference between fat and fibroglandular tissue and ductal tissue through here. Ultrasound, this is a very zoom-in ultrasound of I think a cyst of some description. But the idea is that you can just looking at these images, obviously they look a lot different in terms of the types of things that they show and the contrast and the resolution of these images. What we would like to do is to use biomechanical modelling to bring all of that sort of stuff together. So this is where our finite element models are useful for looking at or taking care, accounting for those shape changes between these modalities. And if we can embed this image information into our models and then warp the models, we can effectively create mappings between these different imaging modalities and carry along with that the image information. So I'll come back to that point later. And so we do that using the laws of physics. So, well, I talked about this briefly yesterday, but the idea is we take our image, we segment out some interesting information from that image. So in this case, it's just the skin surface and the pectoral muscle surface. We can fit three-dimensional finite element models to those surface data. We can then apply the laws of physics. So this is basically Newton's law of conservation of linear momentum, written down in a slightly different form, in a weak form, which is useful for finite element analysis. We can solve these equations on high-performance computers, and in this case, this is a volunteer, one of the first volunteers that we dealt with here at Camry, at the Centre for Advanced MRI. What we did was we measured the prone, freely hanging breast. We applied a small amount of compression here, so I think it was about 30% compression, to our finite element model. We embedded this image in the model, and we warped the image we're using that finite element model to predict what the deformed breast image looked like. And what I haven't shown here is that we also have the actual image from that 30% compression. So we're able to compare how well does our finite element model do in terms of predicting the tissue movement within the breast. So this is the type of thing that we do. We take the images, set up these models, embed the images in the models, and warp those images to be able to predict where do the tissues move in different positions, different physical sort of situations, if you like. And so, yeah, we're using our local software to do that, some of the stuff that you'll be dealing with. So I showed this pipeline briefly yesterday, and I think you're going to be focusing, I showed a version of this pipeline, it looked a bit different I think than when I showed yesterday. I think you're going to be focusing on this part in this work or tutorial sort of session later this morning. But again, just very briefly, the idea, and I'll show you this a couple of different times for the different applications that we're concentrating on. But the idea is we start with our patient images, we pull out the information, we build these anatomical models, solve some sort of simulation, so compression simulation or prone to supine simulation. We can then visualize those images, identifying the regions of interest that we might be interested in co-localizing between different imaging modalities. We can present that back to our clinical collaborators through some bespoke software or through web browser-based software. So this is the general pipeline. We've got dedicated services that are sitting within the Auckland Hospital here that can push automatically to a gateway that we have in the hospital. We send the data securely to our service here at the ABI. This whole process now can be done completely unsupervised, so we don't have to go in there and manually click a whole bunch of points, which you might be playing around with. We've got all sorts of automated segmentation techniques, model building techniques, simulation techniques, and image warping and visualization. We're still working on this aspect in collaboration with our clinical partners at Auckland Hospital to work out just what would they like to see, how would they like it presented, how can they get access to this sort of information. So this is the goal for what we're working on. And so I'm going to talk about just a couple of applications to begin with, specifically around using soft tissue mechanics, just illustrating really those concepts that I've talked about. And then I want to just give you a flavour of some of the complexity with this problem. So it's easy to describe the problem to you. If you've got any questions, by the way, just sing out. You don't have to sit there, and if you don't understand anything that I'm saying, or if I'm speaking too quickly, or if you've got any questions about this, just sing out at any stage. So describing the problem is fairly straightforward. People can understand what we're trying to do, but to understand just how accurately can we do that, what do we need to be able to do that, it's actually a very complicated problem. We're dealing with really large deformations. We're dealing with complicated heterogeneous organs, so lots of different tissue types within the breast, lots of different types of mechanical properties. The skin is really important. It's anisotropic, it's non-linear. The fibroglandular tissue is generally stiffer than the fatty tissue, for example. Tumour is even stiffer again. So lots of complexity to do with the different tissue types and the different mechanical properties of those tissue types that we need to take into account. And also lots of complexity to do with the large deformations that are taking place. So we cannot use simple linear models, linear elastic models, to be able to solve these problems. And I still review papers even today where people are trying to apply linear elasticity theory to these sorts of problems. Linear elasticity breaks down after about strains of greater than about 0.5%. We're dealing with strains of 30 to 40%, and people are still trying to use these standard engineering techniques, which are good for buildings and bridges and so on, for these soft tissue mechanics problems. It's completely inappropriate. So that geometric and material nonlinearity really throws up lots of difficulty for us in terms of solving these problems and doing it accurately enough to make a difference in terms of the clinical application. So the two main applications I'm going to talk about are what we call prone to supine repositioning. So it's literally taking an MRI of someone lying on their tummy and predicting what does it look like when they're lying on their back. Really large deformations taking place, and trying to do this in a completely unsupervised manner without manual intervention. This is what we've been working on for the last few years in order to make this robust, to make it accurate, to make it fast, so that we can deliver this information back to our clinical partners in a small amount of time. Then the second one, which is really what motivated us originally, was to deal with an even more complicated problem, was to map information from MRI to information from X-ray mammography. And what makes this so complicated is the really large degree of compression that takes place during X-ray mammography. So the numerical methods that we've had to experiment with and to deal with in terms of solving X-ray mammography, we're still working on that. And we've got a couple of PhD students who've been working on this over the last couple of years, and we're still struggling with getting this working very robustly, to be honest. But I'll talk to you about the progress that we've made in this second application. And then I'm going to talk about a number of different sort of steps along the way when we're dealing with this model building. So again, here's another form of that pipeline. This is specifically the pipeline, the workflow that we've set up for prone to supine MRI visualization or prediction of prone to supine MRI. A lot of this looks familiar, but the idea is starting from this prone MRI, going through the automated segmentation, automated model generation and simulation. Now you can see we've got this full torso model. The idea is predicting what does the supine position look like, embedding the prone MRI image into that model and warping that image to generate some results, and then passing that back. We haven't worked on this so much, but this is the general workflow that we're talking about. And so the different steps involved, and this is a postdoc that was working up with us up until relatively recently, very recently. There's a bunch of segmentation steps. So Habib worked on what he calls a supervoxel classification technique, where we can basically break the images up into these collections of voxels. So we've got, I think we've got about, is it 512 by 512 in plane images. They're 1 millimeter voxel resolution here. So yeah, quite high resolution in terms of the voxel resolution within the images. We break them into these clusters of voxels, and the idea is Habib's technique is using a whole bunch of filters for feature detection, a bunch of image filters and a bunch of positional filters as well, but the idea is being able to classify each of these supervoxels now into the different tissue types. So specifically we were interested here in just using this technique to pull out the skin surface and to pull out the rib surface in terms of the segmentation, so that we could build these 3D models. And so there was a bunch of image filters and, like I say, a bunch of location filters that he passed over these supervoxels, but this is one of the techniques, one of many techniques that we've used now to do this segmentation completely automatically, just based upon receiving this sort of image. And that's now working fairly well for us in terms of being able to pull out the surface features that we're interested in, so we can build these three-dimensional models. So that's one of the steps in our workflow. Dwayne Malcolm, who is working with us and is still working with us, in fact, remotely, at least from his nice sunny beach on Rarotonga, is working on how to take those that image segmentation, so that the result of this part of the pipeline here is this surface segmentation here. Now what Dwayne has been working on is how to take that surface segmentation and to automatically build surface representations, now low-dimensional parametric representations of those surface data by using a shape analysis technique, so principal component analysis, to be able to build these surface representations of these dense data. So once we have these surface representations, we can then turn them into biomechanical models by segmenting out the 3D space that sits between these surfaces effectively. So that's the sort of the model generation step that Dwayne was working on. It's a combination of a population analysis. So we're looking at a variety of different shapes. We've now done MRI on about 120 volunteers ourselves at Auckland Centre for Advanced MRI. So we're able to run this sort of analysis on about 80 of those volunteers. We also have about 230 clinical MRI cases, which the images look a lot different in terms of the clinical MRI. They don't tend to get the full torso, they just have the localised breast regions. But what we're doing is we're using our shape analysis techniques from our volunteer database to be able to fill in the missing information from the clinical database. So we're dealing with fairly reasonable sized data sets to be able to test out these techniques. The main idea with the shape analysis is to ensure that in our volunteer database we have a wide variety of different shapes, and that our models can represent these different shapes, such that when we get a new unseen image and we want to generate the three-dimensional representation of that image, effectively we can interpolate between these different modes using this automatic principal component analysis fitting sort of technique. So we can use that PCA fitting to get a really good initial estimate for that new unseen volunteer. Once we get that initial estimate of those surfaces, we can then use local search techniques for looking at gradients in the images to be able to refine those parametric models to that specific individual image. So it's a combination of a population-based approach to be able to get a reasonable initial estimate for the geometric model for that new individual, and then we follow that with a non-linear geometric fitting approach with local image searching methodology in the region of the initial model to be able to effectively tighten up or further personalize that model to the individual image.
One question?
Yeah.
Why did you choose PCA? Because it puts a constraint that the variants have to be orthogonal to each other?
The modes are orthogonal, yep.
Why not like independent components?
Yeah, so I mean the idea of PCA or ICA, we could use our ICA. PCA is relatively convenient and easy to use in this sense. We haven't actually done a real thorough investigation as to which method would be better for this sort of approach. But I think the orthogonality of the modes can be of benefit for this sort of thing, because you can add one mode at a time. You don't need to refit those parameters for those earlier modes. So we can determine relatively straightforwardly how many modes do we need for a given individual. But the PCA part of this, or if we were to use the ICA, the shape analysis part of this is really just to get a reasonable initial estimate of the model. We still go back to the original image and start from that initial estimate and do a full finite element non-linear fit to get the final model that we will use for our biomechanics analysis. But yeah, there are a range of different techniques that we could use, and we haven't really done a thorough analysis as to which is the best, the fastest, the most accurate. But for the purposes of this, like I say, it's an initial estimate that we're after relatively quickly, relatively easily. And then we always do that final sort of final nonlinear fitting, full finite element fitting sort of methodology at the end to get our final model. So yeah, that's where we're at with and you're going to talk about some of this stuff with, well, at least step through some examples with model generation for this tutorial. So then Prasad, he's just finished his PhD with us. His job was to really take those parametric surfaces and to turn them into a biomechanics model. So Prasad's expertise is in soft tissue mechanics modeling, so finite element methods, but also model calibration techniques. So looking at how to pull out the stiffness properties, for example, using different types of imaging modality. What are the identifiability of those material parameters, those stiffness parameters? How can we perform experiments to be able to pull out those parameters and make them representative for a given individual? But in terms of our clinical pipeline, Prasad set up methodology now to take those surface representations that Dwayne had developed and develop full 3D finite element models of those surface representations that we can use for biomechanics applications. So going from here, the surfaces on the left, to the full sort of 3D model on the right. Locally, we tend to use higher order elements, so we use cubic Hermite interpolation functions, which gives us this smoothly continuous surfaces. So when you see other groups working in this space, you'll see usually hexahedral trilinear elements. So you'll see many, many more elements in terms of the element discretization. The numbers of degrees of freedom that we use are about the same as others use in this field, but we use these higher order interpolation schemes. So people always ask us, why can you get away with just so few elements? Surely you're numerically inaccurate. But no, we've been through the numerical convergence in terms of the spatial convergence to be able to represent the geometry, but also the solution convergence. How accurately can we predict the deformation patterns? So this is the sort of discretization scheme that we need with these cubic Hermite shape functions to be able to reliably predict the deformations of the breast. And so this is a very old movie now. We haven't actually generated it for this, but the idea here is, and I can't stop it because it's an animated GIF, but the idea here is that we start from this prone position, we embed the image, we may identify some kind of region of interest. This is just a fatty region at the moment because it's on one of our first volunteers, but it may be some sort of interesting region of, say, increased blood flow or some suspected tumour sort of tissue. The idea is that we can basically, in a two-step process, take account for gravity. So we need to make it a two-step process because what we first need to do is unload gravity from the prone position. We then need to load gravity in the other direction. And it's not as simple as just taking gravity and applying it twice in the other direction. There's an unloading step and then there's a reloading step. And again, I've reviewed papers where they've said, oh, we can just take gravity and apply it twice in the negative direction to simulate this. You actually get the wrong answer in doing that. So it's a two-step process to be able to predict what we call the unloaded reference state, which is what you need for any sort of mechanics problem. You need a well-defined, stress-free reference state that you can use with which you can refer strain tensors to. So the idea of taking this model is to generate that reference state in the first step, turn the model over and apply gravity as a forward sort of loading condition in the second step, and embed the prone image into that the prone reference model, and walk that image through this two-step process to map now, or to predict where does that region of interest move to when I go from the prone position to the supine position. And so in this case, one of the things that we need to do, and we haven't been through the calibration step for this particular model that I'm showing you, but one of the things we need to do is to estimate the stiffness of the breast, the stiffness of the different tissue properties. So this to me looks slightly unrealistic because probably the breast tissue stiffness that we've chosen for this simulation is probably a little too stiff. We might expect the breast to be move slightly further around or slightly flatter to the chest for this sort of individual, but the model calibration is really important to be able to get those predictions of motion to be accurate. So yeah, we haven't actually done that for this particular model at this point. And so then I've talked in brief terms and just showing it in a slightly different way. The idea is starting from the prone position, segmenting out an interesting sort of region of tissue, embedding that into or setting up our prone model completely automatically. This is a manual step in terms of marking out this region of interest that the clinical user might want to do. Set up the model, embed that region of interest in the model, predict where does it move to in the supine position, and then identify that same region of interest in the supine position. So this is just a different way of showing you exactly the same sort of thing that I've animated on the previous slide. And so we're still working on how to develop the user interfaces now that the clinical people can quickly sort of mark positions here and automatically kind of update these sorts of things. We're using WebGL sort of technology that the software group are developing for us as well, or for the ABI, but we're using that, taking advantage of those developments for this sort of approach. So that's the first kind of pipeline that we're dealing with. And why are we interested in doing that? I mentioned at the beginning, it's one of the things that the clinical community want to do is to really understand how do the tissues move, where do they move to when you take the person from lying on their stomach to lying on their back, for things like ultrasound imaging, finding that same tumour that you've seen something in the MRI, trying to find that tumour using second-look ultrasound can take them somewhere between, for small tumours, somewhere between about 30 minutes and an hour. So it's a really long time, and you're poking around. It's sort of an invasive procedure, the ultrasound procedure, and it's very difficult sometimes to find that the same feature that they've seen in the MRI. If they've got the MRI right in front of them, they're hunting around in that region in the breast. What they're doing is trying to find that same lesion. It's got very different contrast in the imaging. What we're trying to do is to help them determine where to look with the second look ultrasound sort of procedure. Also thinking about things like guided biopsy. So taking biopsy is normally done with the person lying slightly oblique. If we can predict how the breast changes shape and predict where do those internal tissues move to, then we can help with ensuring that they're looking in the right sort of position when they're taking their tissue samples, to make sure they are indeed sampling the piece of tissue that they think they're sampling when they send it off to the lab. So they see something in an image, I want to get a bit of that tissue that I see in the image, make sure that they're looking in the right position in the different position that they're looking at. So make sure they're sampling the tissue from the right location, I guess. So this first application is really to assist the clinical community with those difficult problems. The second application is a similar sort of thing, but it's mapping information between the 3D MRI and a 2D X-ray mammogram. So again, the workflow is fairly similar. What we start with in terms of the input data for this application, again, the prone MRI, this is what the image looks like. We'll start with a craniocaudal view of the X-ray mammogram. So X-ray mammography, they're compressing the breast this way, the craniocaudal direction, also the mediolateral oblique direction. So two images of the compressed breast. I'm just showing you one of them here. The idea is that if they see something, and this is an actual image now which they've identified, sorry it's a little small there, but they've identified two little lesions here which obviously look a whole lot different to the rest of the tissue. The only reason they look different is that we got the clinician to draw some little red markers around them. When I looked at this, I certainly wasn't able to spot these things of interest. But they've got two markers here, or two regions of interest I should say, and they're interested in finding out, well, where in the breast, in terms of the MR images, where can I find those same lesions? So again, the same first couple of steps in terms of the segmentation and the model generation aspect is exactly the same as before. We're dealing with the same images. Instead of doing the prone to supine calculation, now we unload the breast to calculate the reference state. We now stand the person up and we compress the breast between two plates. And what we can do now is, and again, embed that image into that compressed model, and we can use the laws of X-ray physics, or the physical principles associated with X-ray physics, to actually predict what the warped MRI will look like in terms of a mammogram sort of situation. So we can take this image, we can use some knowledge of the X-ray sort of imaging procedure, the physics of X-ray imaging, to be able to go through an image processing kind of pipeline to actually take that image and predict what does the mammogram look like. So this is a predicted mammogram. We can then compare that prediction with the actual mammogram and do a two-dimensional local registration approach to be able to determine how to map every single point in this 3D image to an equivalent point in this 2D projection here. So there's a bunch of image processing in terms of generating this visualization here. And again, we can send that back in terms of a clinical user interface. So we might have the two views here, we might mark something on one view, use our three-dimensional representation to predict where does it appear on the other view. I'll come back to this idea a little bit later. But the idea here is that we can use our biomechanical models to represent the compression simulation. We can embed the MRI into that compression, we can warp the MRI due to that compression, and then we can set up effectively a ray tracing procedure through that warped MRI to be able to predict what the mammogram looks like from this set of 3D image intensities here. So we generate a pseudo mammogram, we compare that with the actual mammogram to see how well can we map features of interest between MRI and the mammography. And so yeah, this is the pseudo mammogram, this is the actual mammogram. The idea is we now have a reasonable degree of certainty that something that I haven't actually got the segmentation here, but something we've segmented here predicts it here. We can then look locally to say yes, we are looking at the same feature effectively by mapping geometrically between those cases. And so I'm not sure if these movies still work, probably not. I've got another one a little later. The idea is, again, setting up these geometric models, building these models, warping the images to be able to do that. So hopefully this one works. Oh yeah, okay. And so what we're looking at here, this is a simulation that Jessica Jaw, when she was working with our team, developed. What she's looking at here is just predicting where do a series of material points here in the reference case, where do they move to as we bring on the compression. So that you're looking side on at the breast, there's the pectoral muscle surface, here's the fixed plate at the bottom of the mammography machine, there's the moving plate, the paddle that comes down. So actually we've moved this one up in this case and then we hold it. The top paddle comes down, and what we're showing here is just the displacements associated with that set of material points that we embedded in our reference model. We were interested in how far do the individual tissues move and how heterogeneous is that pattern of deformations. The color code here shows us the length of those vectors. And so we find that we're able to look at the displacement of the nipple. We can look at the displacements of these material points and determine how those tissues kind of spread out, how they warp in terms of the deformation patterns. And this is something that was interested. She set up this simulation for a company that we're working with in Wellington who are interested in the degree of pressure that mammography paddles apply to the breast. So we're able to predict that pressure distribution, but then also how does the tissues spread out in the immediate vicinity of the paddles. How difficult is the skin to model in that region? So we're looking at a whole bunch of different sort of applications to do with compression of these 3D breast models. And so I've got this slightly out of order, but just back to the mammography calculation. The idea of mammography is we actually have two views. So these are two projections through the same breast. So these are an actual case, a breast cancer case that we're looking at. There's the craniocaudal, the head to toe direction. Here's the mediolateral oblique, which is shoulder to hip, the second direction. The idea is that in this image there were two suspicious features. In this image there's only one. So first of all, are they the same thing? I mean, when I still look at this now and I can't really see anything there. I know it's obscured a little bit by the boundary that's been drawn on that, but the contrast of that part there doesn't look a whole lot different to me in terms of what's going on around it. Now, the people that read these mammograms, they're really experienced, obviously. Why aren't they marking things up here, for example? What's going on up here? There's all sorts of complexity in this image that the readers are very, very experienced and very good at, but it takes a whole bunch of training to get to that sort of level, and there's a whole bunch of uncertainty associated with reading these mammograms as well. So it's easy to understand why small cancers are missed when it comes to looking at these sorts of images. But even just marking these images like this, the question for me initially is that the same as that, or does this bit of tissue correspond with something that's going on up here? The second question, we've got two of them here. where's the other one gone? Where did it move? So there's all sorts of complexity with this, and what we would like to do is take away some of that guesswork. And using it's a simple idea, the mammography, with these two different views. The idea is that, and this is what the clinicians do, they put these images up on the screen, and in their head what they're trying to do is register this information in terms of a three-dimensional representation of the breast. So they can see the patient in front of them, they've got these two images up the top on their view screens, and they're assembling this image in their head as to say, well, where are those features of interest? How do they relate to each other? Are they the same thing? What is the three-dimensional sort of characterization of this person's breast? So that's a triangulation exercise. They're able to predict back through to determine if those features co-locate in terms of the 3D breast. They're very good at doing this, but you can understand why it takes a whole bunch of experience and a whole bunch of training, and why things can go wrong, particularly with small cancers. So our contention is to take away some of that guesswork, at least, by using biomechanical models and the laws of physics to be able to predict these things in 3D. So I will just stop this one. This is another case where we're dealing with microcalcifications in this case. So X-ray, can I go back further? Oh no, we've already marked them. Underneath here, you can't actually see it, but there's actually some quite bright white spots, which are these very, very dense bits of calcified tissue that usually sit inside the ducts. Individual calcifications are fine. It's when you get these clusters of calcifications which are early warning signals for breast cancer. There's probably a couple more very small calcifications in these sorts of regions here. But in this patient, they spotted 2 microcalcifications in the craniocaudal view, and they spotted 3 in the mediolateral oblique view. So we were using this as a way to help us understand how models work. But I mean, the immediate question is, well, which one? How do you match these up? There's only 2 here. There's 3 here. Where's the third one gone? And which of these 2, if any of them, align with these 2? So how can we use our biomechanics to help us with that situation? Well, we can build 3D models of both of these cases. And so this is work that we did quite a few years ago now. But just to see, the idea here is that we're dealing with a compressed 3-dimensional breast. The X-ray is taking a photo through that breast. What do those individual markers kind of look like? They could be any kind of candidate point through that 3D compressed volume. So this is the craniocaudal view on the left. Here's the mediolateral oblique view here. Again, any of these individual material points through the 3D compressed bottle could represent that image. We've just overlaid the X-ray image here, but it's actually a conflation of all of the tissue points through that 3-dimensional thickness. So it's a projection through that thickness. So the idea is that we can take candidate points through our 3D thickness here, and those 2 purple, candidate points in terms of the 3 orange points here. So those are the potential candidates. Whoops, it's jumped past it already. Do I have to play? If I crashed it, have I? Try that again. Bring it together. There we go. So this is now just showing us in the mediolateral oblique view. Have I changed the colours there? I think I have actually. Sorry about that. In the previous view, these vertical ones were purple. Now they're orange, and so I've swapped the colours inadvertently. In the mediolateral oblique view, you've got the straight lines of those 3 markers. We have the curved lines now for the equivalent craniocaudal markers, and you can see now we've got these intersection points here. So these intersection points tell me that these are likely the places where those 2 markers, those 2 calcifications in the craniocaudal view are located in the 3-dimensional breast. We can then back out that compression, and we can determine now where are those markers in the 3D reference breast. We could effectively take this, put the person lying on their back, and predict where do those calcifications move to in the supine position, or we can put it in any other position. So that's the co-localization of information starting from two X-ray mammogram images. Now the difficult part with this is that we still need a 3D representation of the breast. So for this sort of application, we're thinking about just using surface scanning of, say, the person standing up and perhaps lying or standing, leaning forward, for example. We still need this 3-dimensional shape that we can use to generate these projections and to do this mapping in 3D. So there's all sorts of geometric modelling associated with this application. I've talked about this one already, mapping from X-ray to mammograms in terms of that workflow. But again, just to say, we can predict what a mammogram looks like, and we can compare that with an actual mammogram, do some local image registration to tune some of these model parameters to do a better job of that registration, to set up now a full mapping all the way from the 3D MRI to the actual 2D projected mammogram. So again, that was stuff we did a while back. Okay, so we've talked a lot about the different applications. Why is that important? Well, I've already mentioned to you about the imaging modalities tell us different information. They look a lot different. So using these biomechanical models is helpful for us in terms of bringing different types of clinical information together. How are we going for time? How long have I got? 10 minutes? Okay, cool. So this is just a collection of slides that I threw together last night in terms of the stuff that we've been working on. A little bit more about the shape modelling. So we've got a reasonable sized database now where we can set up these models. I talked a little bit about the principal component analysis for the skin surface. We found that it was really important to be able to use some landmark features to get this automated analysis kind of working well. So the features we ended up using were the nipple positions, the sternal angle position, and I think the spinal cord position. So this gives us a general kind of size and shape of the torso. The nipples are obviously very local to the breast, but with just a small amount of additional landmark information for a given individual now, we can get these principal component analysis models to actually do a reasonable job of segmenting now the entire skin surface, just based on a very small amount of information. And so what Habib looked at was, well, we don't want to have to go through images and manually find the nipple, bang, click, 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 click. Can we use template matching? So based upon our database, yes, let's manually find that, and I think we did it in about 60 cases or so. And in the region of those landmarks, we've got small amounts of image information that we use a principal component analysis on those template images to be able to use that now to identify those features automatically from a given 3D image set that we're given from MRI, for example. So in a completely unsupervised fashion now, we can automatically find these anatomical landmarks. We can use those anatomical positions now in our principal component analysis to get this full 3D surface segmentation of the skin. So this is stuff that Habib worked on in terms of how to use this template matching approach. For a while there, we were having to kind of go through click, 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 just a small number of points. So it was relatively quick, but we wanted to get that away, take away that task, if you like, from our clinical community to be able to do this. So this is working pretty well for us. If we didn't use that information, then the PCA models it does struggle quite a lot, particularly with actually getting rid of the arms. So you'd think that'd be straightforward to exclude that. There are other ways that we could perhaps deal with that. But there was bleeding really from one surface to the other, so it would jump across onto the arm surface in certain circumstances when we didn't have this localization information involved. The other thing that Habib has been working on is using different sort of classification and segmentation techniques to be able to pull out the differences between fat and fibroglandular tissue now within the breast, because we've got good reason to suspect that the models that I've shown you until now, we're treating the breast as being this one homogeneous mass of tissue with one single stiffness parameter, but we know that the properties of the fatty tissue are softer than the properties of the fibroglandular tissue. So in order to improve our estimates of biomechanical model predictions, we think we need to take into account that difference in stiffness. So this is the latest sort of techniques that Habib was working on in terms of how to segment out those different compartments such that we can assign different material properties to those compartments. So he was using k-means, but he looked at a bunch of different techniques, expectation maximization, I think fuzzy C-means as well as different classification techniques for these different tissue compartments. The latest thing we've got a Part 4 project working on at the moment is using artificial neural networks and deep learning sort of techniques So the complexity with the model, and what is really important, is what is happening to the underlying muscle structure. So when we rotate our shoulders back, and we see this in our MRI images all the time, we kind of ignored it for a long time, but when you've got someone lying prone in an MR, their shoulders are kind of rotated forward. If you take them and lie them on their back, their shoulders rotate back, and you've got this massive sliding of the pectoralis major muscle across the pec minor. And so there's this massive change in the shape of the pectoral muscle, and of course that's going to affect the change in shape of the breast as we go from prone to supine. So we ignored it for a long time, but we now have methodologies. Well, and we ignored it because it was actually a really difficult thing, and I probably should go back to one of the raw images, but the contrast of the pec muscles looks very, very similar to the contrast of the fibroglandular tissue. So simple sort of thresholding techniques and so on, they never really worked for us because we were unable to really distinguish the muscles from the dense tissues of the breast. Using this deep learning network based upon a training set, we've got about 60 cases where we've manually segmented the pec muscles now. This side of artificial neural network sort of approach looks very, very promising to be able to automatically identify now these pectoral muscles for us, so we can build that information and increase the fidelity of our biomechanical models as well. And so then thinking about actually how do we get those mechanical properties, this is work that Prasad did for his PhD, by combining knowledge of measurements of the skin, the nonlinear anisotropic properties of the skin. Prasad was able to build that into our biomechanical models. He also looked at just moving from prone to supine. We've got lots of MR images in the prone and the supine positions. So can we use those detailed MR images to actually calibrate biomechanical models for that particular individual? So if we use the prone and the supine image now, MR images, can we build models and estimate the different stiffnesses of these different compartments using those image information to be able to determine or to calibrate those parameters? So what Prasad found again he had to do was to do more than just matching the surface shape of the skin surface and the surface of the muscle here. So that's the pec muscle in red, that's the tissue mass in orange here. He needed more than just the surface descriptions of those different compartments. He actually needed material point deformations. So he looked at the deformation of the nipple and a number of small material points that he could identify in the images. He needed to use that material point information instead of just the surface shapes to be able to tie down these parameters kind of uniquely for this calibration exercise. And so we also, this is a bit of work that Matt Parker has been doing up in the lab here on level 5, is developing now, well, this is a very old slide, but developing micro-robotic sort of instrumentation techniques. And so there's a force torque transducer here, a 6-axis force torque transducer. There are linear actuators here, and there's a stereoscopic imaging system sitting around the outside. The idea is that we can prescribe known forces and torque to a region of skin. We can do shear deformation, we can do indentation, potentially we can attach this and do small uniaxial extension sort of motions. We can then image the three-dimensional deformation patterns here using a cross-correlation technique that we've been working on over the last decade or so. And so we can get really good estimates now of the local tissue properties in terms of the local skin properties for this particular, using this particular device. Now this is very much an in-lab device. We're working on moving this now into a sort of a more clinical situation by developing a handheld stereoscopic system with a very simple force torque transducer probe on the end of it. And we're in the process of building that probably over the coming, well, the later half of this year. With a recent grant that we've been seeking. So the idea here is to be able to make accessible measurements. I mean, they're non-invasive, but they're invasive in some sense because we're actually touching the skin, but we're not piercing the skin, so they're not invasive in that sense. Clearly, the imaging, the stereo imaging that we're developing is completely non-invasive. But the idea here is to be able to make some detailed measurements for a given individual. We might be able to quantitatively palpate the breast, because this again is one of the techniques that they use to be able to identify tissue masses and track them over time. So the idea is we're taking forward is to use this sort of approach to be able to take out some of the guesswork in terms of the manual palpation that takes place in breast cancer diagnosis. And so there's a whole bunch of other projects, spin-off sort of projects that we've had over the years. We're interested in the friction between the mammographic plates and the breast skin. So we've been looking at how to take that into account, because as the breast compression plate comes down, it comes into contact with the skin. As it touches, there is some degree of sliding that we need to take into account, and just how important that is, it's a little unclear to us at this stage. But taking into account that frictional contact is going to be important. Dealing with these really large compressions is still really difficult for us, and it's difficult for everyone who works in this field. The mesh distortion that takes place for these very large deformations is difficult to deal with numerically. We've got a graduate student who's now working on using mesh-free methods to be able to take into account some of that complexity and hopefully make the solution of our models. Well, in fact, he's already got very large deformation problems working with his mesh-free methods. So we're in the process of hopefully the second half of this year to be able to translate that to our breast modelling environment. There's obvious applications, and we've already had approaches from potential clinical collaborators here in Auckland around planning for surgery, around planning for radiation therapy and radiation oncology. So again, we can predict where the breast tissues move in the supine position when they're doing their radiation planning to fire X-ray through the supine breast effectively. We can help them decide how to avoid the healthy tissues and how to focus the radiation beam onto the cancerous tissues. So they're very interested in this sort of predictive technique to be able to do that. We've had other kind of small projects involved with bra design for sports bras, again using biomechanics and this model building technique to be able to do this, to deal with potential what do breast implants look like if someone wanted to plan to have breast augmentation, or in fact even breast reduction. So very large breasted women go through breast reduction techniques. We can then come up with some sort of prediction as to what their breast will look like following the surgery, if they inject implants or if they reduce the size of the breast through surgical techniques. So again, we haven't done any major projects in this area, but there's very definite applications of this sort of thing. So these are all the sorts of ways that we can use biomechanics, not just for breast cancer imaging, but also for other sorts of processes. I'm going to skip over this a little bit. This is just another slide that I threw in there, and probably in the wrong place. But very briefly, we did some MR imaging with the person wearing a little vest which was filled with water. So this white stuff here is water. The idea is that we were trying to, this is the case where we were taking off the effect of gravity, so we're developing techniques to unload the breast. We needed to make measurements to validate those techniques. So put that slide in the wrong place, sorry. Another thing that Hayley worked on when she was here a number of years ago was just taking image information, and we're just using 3D models here. This is telling us about the position of breast. So they divide the breast into about, I think, 9 different locations, 9 different compartments. And the idea is that if breast tumours are located in each of these regions, they can determine where does the lymphatic drainage occur for tumours in each of these regions. So lymphoscintigraphy is another method to determine whether or not a breast cancer has metastasised and is now sending its signals throughout the rest of the body effectively. So often when they have some kind of lumpectomy to take out a breast cancerous mass, they will often have to also take out the draining lymph nodes if it is metastasised, and if there are problems with lymphatic drainage for that cancerous tissue, to prevent further spread into other tissues in the body. So Hayley set up this clinical interface now using no motion biomechanics here, but just a 3-dimensional model to show, and this thing is still available on the ABI website, to show clinical people what are the prevalence of drainage to each of the different important ductal nodes for a cancer which has been identified in each of these different regions of the breast. So there's all sorts of statistics associated with that. Okay, well, so our team has changed quite a lot actually over the last little while. Here's our current team. There's lots of room for expansion at this point. We've had a whole bunch of people, and I don't have all the names and all the faces here. There's probably about 30 different people that have contributed over the last 10 to 15 years on this project, but we're the guys left still holding the flame. These are our closest clinical collaborators here at Auckland City Hospital. So Anthony in MRI, Jeremy he's the head of mammography, Wayne's the head of breast surgery, Anthony's the head of breast MRI. We're also looking at ways to sort of commercialise some of these technologies through a small company in Wellington as well, who's interested in breast density. And I think, that's it for today. Okay, so any questions to do with that? Covered a little bit of ground, but mostly around biomechanics.
Are you working in current solutions for increase the diagnosis of breast cancer? Because this was like just location, but not just this execution, great work, how to locate it and how it will change.
Yep.
But there is a kind of a way that you're thinking about how to improve the diagnosis?
Well, so we're not, so in terms of automated computer-aided detection of cancer by just looking at images and looking at the edges around X-ray images, that's not an area that we're focusing on. We're just focusing on the localization aspect at this point. We go to they have a multidisciplinary meeting here at the hospital every Tuesday lunchtime. And so they have people from MRI, people from mammography, people from ultrasound, people from the tissue labs, the histology labs, people from surgery. They all sit together and they deal with these complicated clinical cases. And every week we go up there, they have really quite high resolution projectors, kind of like this one. They've got 3 of them lined up. They've got the X-ray on the left, they've got the MRI or the ultrasound generally in the middle, and then on the right they'll have the pathology, the histopathology for a bit of tissue that they've taken from one of these regions on the right. And everyone in the room is kind of, and even myself, I'm looking at the images on the left, kind of doing this and trying to marry up stuff that I see on the left with stuff that I see in the middle. So the X-ray mammography, they always start with that because that's the screening kind of technology. They see something on that, and then they're kind of scrolling through this 3-dimensional image set, whether it be the MRI or they're presenting up multiple sort of ultrasound images, and they're all everyone in the room is kind of going, well, it's that, and it's incredible. Like here we are in 2016, where they still are using a lot of expertise, a lot of experience to be able to say with some degree of certainty that they can't really quantify, as to say, yeah, that thing, we really do think it is this position here in this breast. What we're trying to do is, and they're kind of waiting for us to be able to deliver this because we've been promising it for quite a long time. But we want to take those 2 left-hand screens out of their general clinical meeting and say, well, okay, we'll still show them the actual images, but immediately below that, let's show them this 3-dimensional representation and just show that that geometric mapping from the raw images that they see to what is the degree of certainty, if you like, that those 2 images, those 2 features in the separate images actually do co-localize. And it sounds like it should be a really simple problem, but because of the high degree of non-linearity and large deformations, it's really quite a difficult problem from an engineering perspective, but it's a very difficult problem even from a clinical perspective. Trying to solve mechanics in their head is not trivial. So yeah, we're not focusing on actual computer-aided detection in terms of diagnosis, though. That's a completely different ballgame.
So this still is not implemented within the clinics?
So we're not delivering results back to the clinical community, but our software we've got software and services which are connected to Auckland Hospital. So that pipeline that I show you very much the images are being pushed from the clinical patient MRI centre automatically through our pipeline, and we are delivering results back to that gateway. We're just not showing them to the clinical people at this point because we want to make sure that we can be sure that what we're delivering is with some degree of quantitative certainty at this point. So we haven't delivered the results back to the clinical community yet, but we've been promising this for a couple of years as well, and we're still not quite there.
It'll be interesting to see if they can find, for example, in the ultrasound,
yep.
a quicker they can find.
Yeah, that's right. So we're trying to set this up so that we can actually start to do some clinical trials now to ask the real clinical question: does it save them time? Does it eventually, we want to know, does it reduce or improve the diagnosis and detection of breast cancer, I should say, not diagnosis. So yeah, those clinical questions are still waiting to be answered for sure. But we're not quite there ready yet to let it loose with a clinical user at this point, but we're getting closer. Yeah. Okay, so I don't know if I've given enough motivation to the model building, but I tried to sort of stress that as I was talking. You guys are about to get into some model building, as I understand it.